Welcome everyone. This is lecture 21, Machine Learning from Data, and in this lecture we are continuing our discussion on neural networks. We will begin by looking at something that's known as forward propagation and then look at some technique, another algorithm that's known as a very popular technique known as the backward propagation, which helps us solve some issues that forward propagation most likely will have. So essentially, we'll be looking at these two algorithms that made neural networks as popular as they are and actually made them really popular in the early 90s, late 80s. We'll also talk whether we are fitting or overfitting the data and what can we do about that. So let's begin. Okay, a quick recap, and I forgot to have that as the title. Well, that's fine. In the previous lecture, we talked about MLP or the multi-layered perceptron, and we use that to derive something that's a well-engineered network, I would say, and that's known as the neural network or NN, as you can see up here. Well, we discussed or summarized this notation here and dug deeper into a single node of any hidden layer here. So let's say maybe this one or this one, and then looked at the specific notation that lets us define that node and understand what's happening in that node. A high-level idea here is that it's this node gets an input that's denoted by S, and it converts it to some output that's denoted by X, and the dimension of S and X are decided by the D's, or like the number of nodes essentially. And obviously because we'll have like one input signal for each node, and then this is a d-dimensional input vector given that D is the number of nodes in that layer L. L everywhere is signifying my layer number. And then eventually we thought of like what the weights are going to be, and we discovered that weights are going to be some matrices, essentially DL minus 1 plus 1 times DL for any layer L incoming, and then for that particular layer, whatever we have, the incoming is always like augmented because that weight is augmented with one more element. That's why this D plus 1 comes in. And so all the weights coming into the layer are denoted by WL. All the weights going out of the layer were denoted by WL plus 1. Dimensionality was almost the same. Why like were we doing all this? Well, the important outcome of this is that we wanted to find out how to get this h of x. That's where everything began. And so in order to get that, we have to compute the weights in the entire network. These W's are important, and we need to figure out a way to compute them. And today we'll see how we can get these weights. Here, W, essentially WL, is representing all the weights such that like WL is a weight in layer L. And obviously you can tell for every node, like node 1, node 2, node D, you will have like a column of all those weights, like all the inputs that are coming into that node. Right. So all these L weight matrices are all the parameters that we get to choose in the neural network. These are my parameters that define my network. Now, if each of these, like W1, for example, this is WL, so I would have like W1, W2, and so on, WD, WL rather, right? Because we said that the last layer is an L, so that's why I'm calling it WL. So once like we have these matrices, and if we specify these L matrices, that's all that we need for my neural network. That specifies or that describes my network, that describes the architecture, that also describes like how the nodes and everything is placed. And so this is an important aspect of my neural network, and I should be in a position to be able to choose these. And how do we choose them? Well, we fit the data, and that is the focus for today's lecture. So let's move on to what's the focus. So here is the neural network again. And again, I'm repeating a few things, of course, because these are important. First layer is the input layer that has like my input data, essentially the features x1, x2, and so on. So I will get the actual values here, right? And it's augmented with 1 because like each of these lines will have the weights, right? And the next layer has like 3 nodes that are computing the perceptron. So we have like these different colors, like as you can see now, the blue, the red, and the green. Consider them as like red, green, and blue perceptrons on the input. So we have like red weights, green weights, blue weights, and we save them in the weight matrix. For example, here it's going to be W1, right? Because this is because this is layer 0, and so this is layer 1, and so this is W1, correct? That's what we discussed in the notation. Now the second layer has an output vector, and the second layer will have the output vector after we have like summed up the weights and then like done some kind of computation with the sigmoid and so on. Well, regardless, we'll still have these weights and we denote them by W2, right? And the perceptron here in a way is the red and the blue perceptron that gets like saved, that perceptron gets saved in my W2. Similarly, the weights for the next layer get saved in my W3. All right, so this is what we were talking about when we said like my entire set of weights, like these matrices, they will define my neural network, because once I have them, I know how many nodes I have, I know how many inputs are coming to each node, and that's all I need to specify the architecture and the overall flow of things in my neural network. So in other words, my h of x, which is the important quantity in my problem, it depends on these weight matrices and my x, of course, right? These x's and these weights. That's all it depends on. All right. So if we look at like a very generic framework for any node and like focus on one node, let's look at what we are exactly trying to do. For example, let's say I have like this neural network that has some input here, and it's a large network, and then I have like another layer here with some nodes, and let us assume I'm focusing on this particular node, right? And it has a theta here, so the sigmoid essentially, and it has some input coming into it and some output going out of it, right? And based on our notation, the input is going to be this signal, and if this is the ith, by the way, in layer L. This is some layer L. So obviously this layer is L minus 1 and so on. All right. So this is my input signal, SIL, right? And if you think about this input, and for example, if there are like DL nodes here, there will be DL inputs from the previous layer to this node, right? And what we do is we take all these inputs and put them in a vector, and then we call that this SIL, right? And for every node, you'll have one SIL, like the I changes essentially for that layer L. So what I'm trying to say is that we will have something that is specified. Let me write it here, a vector SL that specifies the inputs for this like layer. For example, for input for node 1, and I think we saw that like in the previous lecture as well, if I remember correctly, but just to kind of repeat for L. Okay, fine. Now next, something that if I remember correctly, it's XIL, and that is telling me that this is the output. And just like the input, right, I will have the output, except that there will be that augmented one that gets here, in which we don't like really send like the inputs, but it is a contributor when like things come into a node. So that is captured in my xi. And so the x, or the output, is going to be my 1 and then x1 L, x2L, and so on, xdl, right? And the dimension of this one is going to be dl plus 1 because of the augmented one. Okay, so this is a specification, and we know that like we'll have some kind of like a perceptron essentially coming in, right? And then like going in here, and maybe coming in from here and going in here, and from every node, of course. And so we'll have like these weights WLI for this one, and my WL, which always, as always, exists here, will have like that matrix will have one of the columns as like W, if this is the ith one, right? And so this is going to be that, just like a reminder. All right. So now how do we compute the input, my S? And then how do we get the output? All right. So we will compute a perceptron from the previous layer's output, obviously, right? And I know that the dimension of my previous layer, for example, in this case, my previous layer, if this is like L, so this my previous layer is L minus 1. And so the dimension of the input that's coming from the previous layer is going to be dl minus 1 plus 1, right? And that's why I was like emphasizing a little bit on the weights, because I can have like 1 here and then the rest dl minus 1 from the rest of the nodes, and then finally this augmented one as well, right? So if you look at the weights for layer L, right, there is one weight vector for every node stored in the weight matrix, that's WL, correct? Or in other words, let me write it here, I don't have space left. WL is, as I said, W1 for node 1, W2 for node 2, and WD for node D. And each of these, if you remember, is a column vector. Why? Because as I just said, each one of them will have like this dimension. Because I have like things coming from my previous layer as well. And that's what the weights are essentially, right? And each of these is essentially a perceptron, as we just saw, right? And they have the augmented bias, so that's why the dimension is d plus 1. What about these columns? These columns here. So this is like d-dimensional, right? So the dimension here is d, because I'll have like d nodes on which I'll calculate the value. So basically my input calculation has something from the previous layer and something from my current layer, right? And so now I am in a position to mathematically define how we can propagate this information that's coming from the previous layer to the next layer and then to the next layer and so on. Essentially, like what exactly do I want to do? I have like these x's here, right? x1, x2, xd. So I want to propagate these because this is like my data and this is what should be used. So I want to propagate that forward in the network until I get my h of x, which was this, right? And so in order to do that, I'm going to use an algorithm that's known as the forward propagation algorithm. So let's use that forward propagation algorithm. And let's see how that works. It's pretty intuitive, nothing great about it. I think most of the idea here has already been clarified, but let's see why we need to use this. And the very first intuition is that we don't have a convenient formula to compute h of x. And if this is like really, really complex, then you can imagine what my h of x would look like here eventually, right? And so in order to get a mathematical form to that is not as convenient. And so that's why we can do that, but that will become unusually complex. So we need some kind of a heuristic or algorithm to deal with that. Next, we can compute the set of weight matrices, because we said that my weight matrices are the ones that are going to help me do things, right? So what do I need? I need all these weight matrices at every layer. Layer 1, sorry, this is not L, this is 1, layer 2, and layer 3 in our case, right? If there are 3 layers only, so I just need to calculate these weight matrices. Now, these weight matrices have, as I said earlier, they have this embedded in them, the dimension of the layer that's before them and the one like at that point. For example, this W1 has the information of the previous layer, which is layer 0 and 1. This one has the information of layer 1 and 2. And this one has the information of layer 2 and 3. Right, so it is some kind of embedding, because that's how we're calculating the input and then getting the output. So if we know the weight matrices just by like looking at their dimensions, right? If we just like know their dimensions, as is the case here, then we can like reconstruct the network. Because essentially I know the network if I have the ability to know the dimensions of my weight matrices. And implicitly, by specifying weights, we can specify the entire network. That is both the architecture and the values. So that's what we can do. And let's see how we can do that. And I'm going to begin by like focusing on just like one of the nodes. Let's say it's my theta Li. That's just like one node. And so how do I get my SIL? The input for this node, in that node obviously exists in layer L. Well, the thing to think about in this case, that this is going to be the ith column of the weight matrix applied to the output of the previous layer, right? And so the previous layer is already sending for me the x's, and I would have applied the weights that are coming here. And the way I can do that is by using WIL transpose, and we'll come to that in a second, L minus 1. Why? Because these x's are coming from L minus 1. This here is my linear signal. This is my linear signal, which is all fine. This here is my weight of my perceptron that is calculated on this node, right? So weight of my perceptron at this node, right? And yeah, that's it, right? And x's are the values that are coming from my previous layer. So now let's look at this vector SL, because SL will have these components essentially, right? And as we said earlier, how can we calculate SL for this entire layer? Now SL has like these components, which again I'm repeating were like SL1, S2, sorry, yeah, S2 for node is down and layer is up. Yeah, I was just like getting a little bit. Yeah, L has to be the superscript and the subscript will determine my node number, right? So this is DL. All right, the important point here is how will we calculate them? How will we get them? So the way to get them is that the first one will be calculated, as I said, using this formula here. So I will have here the weight W1L transpose, and so this is going to be a row multiplied by my XL minus 1, right? And again, I'll have W2L transpose X, and I won't write that again and again because this is going to be all these rows for all those nodes, and so eventually DL transpose multiplied by my XL minus 1. And so my signal, maybe write it here, right? So my signal SL will be computed by using this entire WL for that layer transpose times XL minus 1. All right, so we can compute the entire entire input signal by one matrix multiplication. Now this is really useful because now we can focus on this computation and build algorithms around this to speed this computation up, because that's all we need. Well, we might say that what happens to the output, because we also need the output. Well, yes, you can just like, because you have SL, your XL, which is based on that, would be of course augmented as we've argued before, and is going to be the theta applied to my S of L. That's all that my output is going to be. So apply sigmoid to the input, get the augmented output. That's it. Now, next, and so this is like nicely summarized here in this, like how do we calculate the linear signal and how is it related, the transformation that happens to get the output. But all of that is good. Now what we need is that we need an algorithm to eventually come up, right, with this final like sort of result that we are after. And so that algorithm is the forward propagation algorithm, which I'm going to write step by step. So how do we begin and how do we end? And let's begin with that. So the forward propagation algorithm, let me be short a little bit. So first thing is like a few assumptions. We are given the weights. We are assuming that we already have these set of weights, and we'll come to that, like how and when and all that. But let's just assume that we have like these weights that we need, and we also have the input, that's my data, right? So let's say we have like W1, 2, and so on, layer 1, layer 2. For all of them, we have them. Let's say all the weights that we need, we already have them, right? And so not even have the ones. I'm just like assuming I have these W's at every step, essentially, right? And I also have my X, which is like my input. Well, this is the case that like I usually have it because I have my data, right? So that's given to me. So how does this work? And what is our goal? So my goal is to get my h of x. That's the goal. And how do we achieve that goal? Well, we begin by initializing as always. So I initialize. And how do I initialize? So I set some x0 equals x, let's say this is like my first input, where my L is also my 0. So I'm beginning with the very first layer. Everything is fine there. And then what I have to do is in step number 2, I propagate. And how do I propagate? Well, I set my L to be equal to L plus 1. That's the next layer. And now I need to compute the input to this next layer, which I know how to do because I have the formula for that, which is SL and WL transpose XL minus 1, which I already have, right? And so we are assuming we have this, right? And we know that we got this from our initialization step because we also have that from the previous step, right? And then next what I need to do, because I have SL, I know I can apply the transformation and get my 1 and theta SL. I can get this, right? And then what I have to do is keep like repeating this, like updating my L until I get this XL. And L, remember, is the final layer. And what this implies is that my h of x is going to be my x1L. What is this 1? Well, nothing to worry. This like 1 signifies your first output. In many problems, in fact, in most of the problems, we have like 2 outputs essentially. Like until now, we've seen just one h of x. And so usually that's not the case. For example, if you're doing classification, you can have multiple outcomes. Think about a computer vision problem where you're trying to segregate multiple outputs, and so you can have like many of them. And so that's why it's convenient to just like write where is it gone, x1 here. Okay, so we basically here we repeat like step 2 from layer 1 to layer L, and then once we have layer L, that is my output. And here it is summarized. This entire process of forward propagation of computing h of x is summarized here. We begin with x0, like use the weights for that and like assuming given weights, right? Calculate some input signal and then go through the transformation, calculate the output signal, and that process goes on and on until we arrive XL. And this is the initialization step. This is the forward propagation step where we are continuously calculating SL and XL, and then eventually end and get the output. Well, all of this seems like really convenient and everything is working fine. But one thing that we have to remember here is that we are assuming that we have the weights. And if you remember, we began with the very problem that how do we get the weights? And so we're going to address that issue in the videos that are coming up. And I'm going to just like end this one now with the forward propagation algorithm.